Well, student, welcome for the in the new module of our video lecture. Till now, what we have studied actually is completing the entire first unit, and today we are going to start the second unit. The second unit basically is comprising the something called local surface inclination methods. There are various methods which are joining together. They all are called commonly as local surface inclination method. We'll study them, but we'll not study them all because we'll try to cover our syllabus, and a few of them are comprising our syllabus, so we'll try to confine our studies only them. A hypersonic is a non-linear phenomena. This we have already discussed earlier. When we say non-linear, what actually we mean is that the result and the cause are not directly related in the linear fashion. So there is no direct one-to-one relation. And this is a normal concept, and which we will not have any difficulty in accepting it, because we know that hypersonic is involving a lot of uncommon phenomena, like something like high temperature chemical reacting flows, and the viscous interactions, and some thin shock layer phenomena. So all these are giving a clear idea that what is going on here is not linear. And if it is not linear, it's not simple. Actually, it's not simple to study, analyze, and put the input into equation. Also, if it's also something like when the Mach number goes high, the basic theory of inviscid compressible flow does not yield the aerodynamic theories which are mathematically linear. That's very simple to understand. At high Mach number, those theories which are actually relating with the high Mach number are not linear. So definitely this hypersonic is not going to be a linear phenomena. This is in a complete contrast to the supersonic flow, in which the linear relations are very much evident. Supersonic phenomena are basically linear. If you recall this Prandtl-Glauert equation, something like this one, we can easily see that the Cp and this theta is the reason, the cause, which is actually influencing Cp, the coefficient of pressure. So because of deflection in the flow, the pressure is actually changing, so we have a coefficient of pressure available here. This coefficient of pressure is caused by theta, and there is a linear relation between these two. This is a constant value, because m square theta is m infinity is a constant value. This is the free stream value. So basically there is a linear relation between Cp and theta. This is what we actually call the linear relation. So once we know the theta, is finding Cp becomes very easy. So all we have to know is just the deflection angle, and once you know that, we can find coefficient of pressure very easily. This is in the case of supersonic phenomena which are linear. This is not happening in the case of hypersonic phenomena. In the case of supersonic phenomena, just one information of theta is enough to find the value of Cp. And once you know the Cp, in fact, we can find all the pressure variation over the surface, and we can find the lift, we can find the drag. So aerodynamic behavior is very easily understood once you know the value of Cp. In the case of hypersonic, this is not happening. So we are not having any linear relations available, but where are some relations which actually are involving the the coefficient of pressure with the inclination of the flow? So if the surface inclination is there, and there is a small deflection in the flow, that deflection alone gives the idea of the surface pressure distribution and the coefficient of pressure. There are some theories and there are some methods which are actually employed to do this kind of linear the inclination method kind of analysis to in the case of hypersonic flow, and in this section we are just going to discuss few of them. So these are the few methods which will comprise our syllabus, something like Newtonian flow theory, and tangent wedge and tangent cone method, and the shock expansion method. In this module, we will study the Newtonian flow theory, and in the next subsequent modules, we'll just see the other two methods also. This whole thing actually comprises our second unit, and the local surface inclination method is actually completed with this thing as far as our syllabus is concerned. What is local surface inclination method? So someone can think about this thing. So the one statement can be actually made it can become definition, but more of a explanation, that the process of finding the coefficient of pressure and solving the problem by just having the information of one local inclination is called local surface inclination method. So it is very simple to understand with this statement I just made, that if you know this just inclination, that how the flow is actually being deflected on the surface, if you can have that value, then this value alone is able to give the idea of the coefficient of pressure. That method is called actually local surface inclination method. So all the methods employing this kind of concept are called local surface inclination method, and basically these three methods are there, which is actually displaying on the screen. These are the three methods we are going to use and study as far as our syllabus is concerned. When we discuss these three methods one by one, we'll do that. We have to keep in mind that we are still discussing the inviscid flow. We are not using the viscosity anywhere. So viscous behavior of the fluid will not come into picture, and the fluid is traveling at the very high speed, the supersonic speed, the hypersonic speed. So we are purely examining the fluid dynamics effect of the large Mach numbers. This we have to keep in mind. So let us first take up the case of Newtonian flow, or the Newtonian law, or what you call Newton theory for the hypersonic fluid or hypersonic flow. In 1687, Newton established a theory which went up to deriving a law of finding the aerodynamic forces on an inclined plane in a moving fluid. This law indicates that the force so exerted by the moving fluid is directly proportional to the square of the angle of deflection. That's why this law is actually called sine squared law. An experimental investigation carried out by D.L. Lambert more than half century later indicated that Newton's sine squared law is not a very accurate law, because they found that it is not giving the accurate result. A lot of the values found based upon this law are actually not matching with the experiments, and then people were misguided by the Newton's sine squared law, that because since if the angle is small, the sin theta is equal to theta, and if it is square it, then it becomes further less, because theta is already small, less than 1, because theta in radian is very very small. If you square it, it becomes further small. So they knew that if the sine square law is applicable, then one factor is very very small, so the other factor they tried to make it large, and that factor was the area on which the lift will be acting. So this, because of the trusting the sine squared law, scientists were actually going for this multi-wing airplane, like bi-wing and tri-wing kind of thing. But later on, D.L. Lambert found that this is not very accurate result, and for the low speed aerodynamics and low speed planes, this is not the law which we can trust and we can utilize. When the same case was applied to the high speed aerodynamics in the hypersonic range, it gave surprising result. So for the low speed aerodynamics, this low speed is actually involving even the supersonic speeds. So subsonic and supersonic both rejected this law. But when the same law was applied for the hypersonic aerodynamics, it gave surprising result. It was matching with the experimental values found by the scientist. So it can be actually really surprising thing that the Newtonian theory developed 300 years ago for the application of low speed aerodynamics amazingly has direct implication to the prediction of pressure distribution on the hypersonic bodies. So as a matter of fact, it actually failed to give the result. It was expected to give the ideas about the pressure distribution and all for the low speed, but it gave the wrong idea. For some reason, it was not actually very much accurate. But this started giving a very agreeing kind of result for the hypersonic fluid flow. In the propositions 34 and 35 of his Principia, Newton wrote Principia, first published in 1687. That's the era and the age and the time we remember for the proposition of this particular sin squared law. So Newton wrote that he modeled a fluid flow and impinged the stream as particles on the inclined plane as shown in the picture here. So he actually he did a small experiment. His ideas were based upon the facts. It's not like he just imagined something and wrote. So he had a flat plate, and then the flow came and impinged on this thing, and then he did some analytical calculations, and then he gave some ideas. So he saw that when this stream came and attacked, and then after attacking, but natural, it is also convincing that the flow stream becomes parallel to the solid surface, and no matter what is the angle of this inclination. So he observed and concluded that the striking the surface particle will lose their momentum normal to the surface, but move tangential to the surface, and hence there will be no loss in the tangential momentum. So he believed, and he actually postulated that all the normal momentums, because this is the flow momentum is a vector quantity, so this velocity can be resolved in two parts. So it will have momentum in two parts. One is the along the solid surface, and other is perpendicular to the solid surface. So he observed that the perpendicular momentum or the normal momentum vanishes, just becomes zero, and the momentum which is actually tangential continues to go like that. So basically what Newton observed was the particle nature of the flow. The fluid nature or the wave nature was not available in his observation. He assumed, and his observation was looking like fluid as attacking on the solid surface like a particle, and then all those fluid particles which are attacking normally just come to rest, become zero, and those who are going tangentially, they don't actually attack, and then just go tangentially and along the solid surface, and they just remain unchanged. This was the observation of the Newton. He made like this, and based upon that he did the analytical calculations, which you are going to see in a couple of. In this in the second figure, you can see that the flow is coming, and this is the area which is actually covering. So this is the area of the fluid which is coming and attacking on the solid surface or the flat plate, and this angle of attack is actually theta, or you can say that the inclination is theta, or this is also the same angle by which the flow is turning, because say the flow was coming like this, and then it turns by angle theta and becomes parallel to the solid surface. So based upon this observation, he made some kind of analytical calculations that the normal velocity which is coming there, so in inlet velocity is v sine theta, and the final velocity is 0, because normal velocity comes to 0. The normal component of the velocity becomes 0, and all the normal momentum is lost. And tangential velocity is actually v infinity cos theta, and that remains same. There is no change in this thing. So in this way, the change in normal component of velocity will be actually this minus this final minus initial. So we have this same thing, something like v sin theta, v infinity sin theta remains there, and the tangential component becomes 0, because this final initial both are same, become 0. And then this is the mass flux or the mass flow rate. So this is rho v, and this is the area. This is the effective area on which the fluid is coming. So cross sectional area of the fluid flow is a sin theta. If you just look at the picture again, you can see that. Here is the picture. So this is if this is the area of the flat plate, then this a sin theta is the cross sectional area with the fluid is coming and attacking on the plate. So the mass flow rate is given by rho AV. So the rho is there, and A is the area, A sine theta, effective area, and the V is the V infinity. So the force will be actually given by the rate of change of momentum. So mass flow rate, this is the mass flow rate, and the change in velocity, So mass flow rate and change in velocity gives back to rate of change of momentum, and that is nothing but equal to force as per Newton's second law, we know very well. So writing force again, now the force is rho V infinity square A sine square theta, by joining those two terms together. So force is basically proportional to the sine square theta, and that's what Newton gave. So it was sine squared law. That is very famous, as a famous sine squared law is there, because force is proportional to the sine square of the sine of the angle of inclination. Now in deriving or analyzing this whole episode, Newton believed in three of the assumptions. These three assumptions are actually that stream of particles are rectilinear. So he believed this all this flow are going in the linear manner, and they just attacking linearly. There is no variation among the fluid particles, and they are not actually they are not even crisscrossing each other. He actually had the macro view that the way a stream is observed, it is going linearly and attacking on the solid wall. That's what he assumed. Newton did not look into the inside the stream, where the fluid particle will have their own motion also apart from flowing along the flow. Second assumption he made is that individual particles don't interact. So individual particles do not interact with each other. So he completely ignored the mutual interactions of the particles, which they may lose or gain the momentum by their mutual interactions. He didn't consider that. So so this is the corollary of the first assumption. If they are all linear, so there is no case of mutual interaction or the collision. And the most it's not ridiculous, but the most important thing in his theorem and the entire analysis was that he assumed that there is no random motion. Every fluid has their own random motion. If the fluid is flowing, then apart from a linear flow or the common flow of the entire fluid or the mass flow rate, there is another motion also available inside the fluid actually, and its molecule at the molecular level, these molecules have a random motion. So apart from that traveling in the same in a direction of fluid flow, they also have a flow here and there, and they on the average they actually flow like a fluid. Otherwise they have random motion in all the directions. And this random motion in all the directions make them just collide with each other. So they have a mutual transaction of momentum. And apart from that, they also collide with any solid surface which comes along. So they also have the impact on this. So not the fluid particle are directly going and actually attacking on the solid surface because of the rectilinear motion. They are also attacking on the random motion. So this random motion he ignored, and that's why there was a small flaw in his theorem, which actually we're going to discuss now. Writing Newton's force again, that sine squared force. Here is the force, total force, the rho VA square into A sine square theta, and this becomes your the pressure, because this is A, the total area. So this force which is acting normal to the surface and divided by area actually becomes the pressure here, force per unit area. So force per unit area basically will be given by this using Newton's sine square law. Now calling this a pressure is giving a little bit a small idea that this pressure must be above the static pressure. The reason is Newton is not analyzing and Newton is not considering the random motion. The static pressure basically is given by the random motion, because when the fluid is static, it's not moving, so there is no momentum change taking place at the macro level. So how the surface is feeling a pressure? The surface feeling pressure because of the random motion of the molecule, where the molecules are in continuously random motion and continuously attacking with the surface, and their direction is getting changed, and they're also interacting with each other, and this is happening even when the fluid is at rest. So the fluid as a whole is not moving, the whole bulk is not moving, but the particles are moving. So this movement of the particle gives the static pressure. So whatever Newton is observing and whatever he has calculated basically is above this static pressure. So he is actually going the dynamic way. So in that case, we can say that the force per unit area what we have calculated based upon Newton's sine squared law is basically the something above the static pressure. So these are the static pressure. This is the total the net pressure at any particular location, and this is the static pressure in the case of ambient condition. So the difference, whatever he has found, is actually the difference. That was very easy to understand, depending upon the fact that Newton law did not consider the random motion of the fluid particles. So if up to here it is clear, then now see what happens. The whole concept become very easy. Now if this is P minus P infinity, that is the pressure above the static pressure, that is equal to the rho Va square sine square theta, then dividing by 1 by 2 rho Va square sine square theta, rho Va square is equal to becomes 2 sine square theta. Now this factor or this parameter as a whole is actually by definition is Cp, the coefficient of pressure. This is by definition. It's not like it's not particular to the hypersonic flow or any supersonic flow or any kind of flow. By definition, this whole collection of parameters are actually is actually the Cp. So Cp becomes simple 2 sine square theta. There is a direct relation available, although it is not linear because theta is still squared here. But there is a direct relation available between the Cp and theta. So one-to-one relation is established, and this becomes very simple to understand that if we can find that theta, that the deflection of the flow when it comes to the solid surface, then we can easily find the coefficient of pressure on the surface. It's really it's a very surprising kind of fact, because at the hypersonic speed we are not even bothering that what is the Mach number. So it becomes completely free of the Mach number. Just the inclination is required. What is going to be the deflection in the local deflection at the surface? That alone will give the idea about the coefficient of pressure. That's how that's what it means actually. This law is actually called Newtonian sine squared law. Also, and any flow which is actually following this we call the Newtonian flow or like that. So normally when we say Newton's law of motion, we normally talk about those three motions which are famous: first law, second law, third law, the law of inertia and the momentum equation and the action of reaction. But these are not the same thing. When you talk about hypersonic flow and then we say Newton's law, then we basically talk about Newton's sine squared law, and that is this, that Cp is equal to 2 sine square theta. Well, Newton did some experiments, and he found something about this thing, and he had one flat plate, and then fluid came, attacked on the surface, and it got deflected by some angle, and by knowing this angle, Newton said that we can find the coefficient of pressure, and also very much evident that this is actually something above the static pressure, because Newton didn't consider the random motion. Now question is, what this all thing has to do with the hypersonic flow? We didn't discuss, we didn't even think about high, we didn't even assume that the flow Mach number is very, very high. We didn't take the limiting value. We simply derived it with the existing mechanics. How this is applicable in the case of hypersonic flow? There is an amazing fact here. Let us see that. So what is the involvement of the hypersonic flow? Actually, a thin shock layer simulates the flat plate phenomena. This is very, very interesting and something which is very particular to the hypersonic flow only. We know that thin shock layer is actually the hypersonic phenomena. So in the case of hypersonic flow, the shock layer becomes very thin, and this thin shock layer simulates the flat plate phenomena. Let us see here. See that the flow comes here and there is a shock available here, and in between we have very thin shock layer available. So if you remember these values for the Mach number 36 and the deflection angle of 15 degrees, the shock layer becomes actually 3 degrees because the wave angle becomes just 18 degree, 20% more than this, more than theta. So it means this shock layer is very thin, and this looks like just the fluid is coming and then it is attacking on the surface and becoming parallel, though it is actually getting deflected and changing its direction just at the shock itself. The shock is so close and so near to the solid surface that it seems, if you have a macro view looking from outside, then it looks like that the flow is actually coming and attacking on the surface rather than getting turned from the shock itself. So it is attacking on the surface and then becoming parallel to the surface. And no doubt the flow in between the shock layer are actually parallel to the solid surface of this wedge. So this is very much similar. What we see here is it attacks and goes there and then becomes parallel. Similar thing is coming here. So by considering this fact, this looks like this sine squared law will be applicable to the hypersonic flow regime, and it is actually applicable, and that becomes a very favorite kind of theorem and the equation which gives the quick result. And then we can actually found that actually this is having a very much close agreement with the experimental results, and that's why these are in picture. These are used extensively in the hypersonic analysis. So So this is our sine squared law. So this Newtonian sine squared law is in effect a local surface inclination method, because we just need to know the inclination and the local surface, and that gives the idea of Cp. This is very simple equation, and we are not going to forget it, because in the case of basic design of any hypersonic vehicle, this is going to be very handy tool. One more fact we have to remember here is that since it is not considering the random motion, and it is not like it's flowing and getting and wetting the entire surface, it's like just impinging. It's coming and like a solid particle, it's coming and attacking on the body, and wherever it is attacking, it is getting deflected, and that deflection is actually causing the pressure to rise. And this fact is also observed that after deflection, the flow has to become parallel to the surface, and all the momentum normal to the surface is lost, and all the momentum along the surface or parallel to the surface is preserved. And based upon this fact, we found that the Cp is actually 2 sine square theta. Now one more thing it is actually being clear here is when we suppose we have to actually find that what is going to be the total pressure rise, the total lift on this body when the hypersonic flow attacks on that. Angle of attack is available here, and anyway that definitely this will not have the same deflection, because angle of attack may be like this, but this will affect locally. We'll have this theta, the deflection is actually local deflection, and this will vary throughout the body. But what the point I want to make here is that when the flow attacks like a particle on this thing, these areas which is dark shaded area will remain unaffected, because the flow will not impinge on this, and there is no random motion we are considering. Ideally speaking, or the factually speaking, the flow goes and glides over this. The flow also wets on this shaded area also, but according to the Newton's law, Newton's sine squared law, flow comes like a flow of a stream of the solid particle. They come and attack on the surface, and they just lose their momentum. They just lose their normal momentum, and based upon that they give the force. They give the pressure and the force. So since this force is this particle cannot attack on the shaded or the hidden or side or the back side of the body, this will remain unaffected. So when we consider try to estimate and calculate the force affected by force given by the hypersonic flow on this particular body, we are not going to consider this area. This is the very important fact we must not forget when we try to analyze the hypersonic vehicles on hypersonic flow and the any body behavior inside the hypersonic flow. The shaded area or the shielded area is actually not considered. It doesn't go there. We'll just take up two cases. We'll see that how we calculate by actually not considering the shielded area. If you don't consider the shielded area, the P or the P infinity, P will remain P infinity in this case, in the shielded area or shaded area which is shielded from the we go in the back side, Cp will become 0 because P will remain P infinity. There is no impinging, there is no the fluid particle not impinging on that, so that remains same. That's what it means. Now let us go a little further ahead for in the case of flat plate case. Here the flat plate, and now this is angle of attack, and the flow comes here and then it attacks on the surface and then it becomes parallel to the surface and loses all the normal momentum. That's what we have observed right now. Now we know that the force, the resultant force because of the fluid is always perpendicular to the surface. This is always in fact locally also, and if it is a flat surface throughout, it becomes a global flat surface also. So we have a flat surface here, and this resultant force can be actually resolved along the flow and perpendicular to the flow, and by definition the force perpendicular to the flow is actually the lift generated, and the flow the force along the flow, dissolved component along the flow, is actually the drag it's giving. And now since the flow is attacking on this side, so this is the behind side, the back side, which is completely shielded from the flow, so Cp will be 0, Cp will be upper side will be 0, so Cp lower will be 2 sine square alpha. That's a very that's the thing we have just now derived according to the Newton's sine squared law. So in this case we have now Cpl is equal to 2 sine square alpha and Cpu is equal to 0. So Cpn will be and Cpn the normal force coefficient will be actually total normal force divided by Q infinity, and the S is the total area. So Cn will be actually Cpl minus Cpu, that's by the definition from the geometry, and dx, and then we just integrate it throughout the length and divide by the C. So this becomes actually again 2 sine square alpha into dx. And then you just since x has nothing to do with the alpha, so its integration C0 to C divided by C will give actually 2 sine square alpha. So whatever we had the Cpl, the same thing becomes actually Cn also. So Cl will be Cn cos alpha because that will remain inclined alpha by the Cn. So lift and this normal force will remain inclined with an angle cos with alpha, so it's actually cos alpha. So 2 sine square alpha becomes into cos alpha, and CD becomes 2 sine cube alpha. Let us just see the picture again to just clarify this relation. Here is the picture again. As we can see that if this is the normal relation, and if this is alpha, then actually this angle is going to be alpha. So lift is actually n cos alpha and drag is n sine alpha, and then n is involving sine square alpha. So actually lift becomes actually 2 sine square alpha into cos alpha, and drag is 2 sine cube alpha. And then we can find the lift and drag ratio also. So that is by just dividing these two becomes actually cot alpha. One thing has to be careful and remember this thing here, that these lift and drag, these relations are actually depending upon the Newtonian flow or the Newton's sine squared law. But this lift to drag ratio is free of that. It's always valid because this is not depending upon the inclination method or inclination process. It's just depending upon the angle of attack. So this alpha is actually basically not the angle of attack. This is the deflection angle. Yes, numerically both are same, but when you just take the CL or CP, we actually take the deflection angle, and then you just resolve into sine cos components. But deflection angle is equal to the angle of attack here, so both are same. So we have to remember this, that CL given by this equation and CD given by this equation are valid when we use only this Newtonian flow and in the hypersonic regime only, and L by D ratio is always valid. So writing again those same things, like you see that. So aerodynamic deficiency has nothing to do with the Newtonian theory. So that's what I just now discussed, that this will be always valid even if Newtonian theory is not applicable. This becomes valid because this depends upon the inclination of the resultant force with the lift and the drag direction. Now what we saw is actually this one angle that we have, just the flow comes and it attacks a flat surface, and there is one angle of deflection throughout the surface, and then we can just find the particular angle, and then we can apply throughout the surface and we can get the CP. We just get the lift and drag also. But if the flow comes to a body where the angle of deflection varies, then how to actually go ahead with this thing? When the angle of deflection is varied, then we go for the local deflection. So the angle of deflection theta will be found by drawing a tangent at the location P, and then the deflection angle is the angle between the free stream flow and the tangent. Take up the case here. This is a 2D variable angle body. The Mach hypersonic Mach number is coming like this thing. The flow is coming with the hypersonic Mach number. It attacks here. Now throughout from here to here, the deflection will vary. How to find the deflection of the flow at this particular location locally, because the CP will affect locally. It's not global value, it's a local value. So when it comes here, we can follow this particular method, that the deflection angle we need to find, to get the value of CP can be found. The deflection, the angle between the free stream flow and the tangent at the particular point. Suppose it is coming and attacking at point P. So at the point P, what is the angle between the tangent and the flow? That angle is the theta angle, because after the impinging, the flow has to become parallel to the surface, so become tangential. So the deflection will be exactly equal to the angle between these two vectors, like that is flow vector and the tangent vector. And then once you know this thing, we can that's the use of our sine squared law. We can find CP, and then we can integrate throughout the surface. And once you know CP, we can find the CL and CD, and once we find the CL and CD, we can easily find lift and drag also. And this lift and drag ratio is actually, again, it doesn't depend upon the Newtonian theory. It's actually always valid, even if Newtonian theory is not valid. Now what happens if the variable angle is there, not in the case of just 2D, it's a 3D. Suppose there is a 3D ogive is there, and then the flow is coming and attacking on this thing. Then how to find the deflection? Because deflection is the only thing we have to find. Once you know the deflection, we can find the CP very easily, and then CL and CD also we can find, and then we can directly find the L by D ratio also. So for knowing all the aerodynamic behavior of the of this fluid flow or hypersonic flow is to know by how much angle the flow is getting deflected locally. This is, in this case, what happens is that we try to find, suppose the flow is coming attacking on P, at the particular location P, what is the angle is actually turning. It's actually deflected from the free stream flow, free stream direction. For this, we just follow one method, like we just go for finding one normal vector at the particular location, particular point P, and then we just try to take the dot product of velocity vector and the normal vector. Then this is given by V. This normal vector is actually the unit vector, so its value is 1. So V, this is the mod V into cos phi, the angle between them. This is not, remember, this is not the angle of deflection. We are trying to find the angle of deflection right now. So this angle is actually the angle between the normal vector, unit vector, and the velocity. So this is the dot product. Now this phi is actually, when this is cos phi, we can write it into sin phi, sin pi by 2 minus phi also. And this pi by 2 minus phi is our angle of deflection. Remember this angle of deflection, because phi is the angle between the normal and the velocity vector, then definitely the pi by 2 minus phi will be the angle between the tangent and the velocity vector, because tangent and the normal are perpendicular to each other. So this pi by 2 minus phi is our actually theta, and we had to know the theta. Once you know the theta, we can find Cp, we can find Cl, we can find Cd as well as L by D ratio. So our requirement is to find this theta, and then this case theta can be given by V is the vector V divided by mod V into dot n. So dot n is something like this, is a unit vector at a particular location. Then we can actually integrate if we have this equation, or if you have the definition of the ogive or the solid surface or 3D surface, we can just find the n at different location. We can integrate this depending upon the situation, but this way we can find the theta, and theta is our deflection angle, and that will give the entire idea about the aerodynamic behavior of the surface in the hypersonic flow regime. So this is not, we are not going to forget this, how we have to find the theta, and the moment we know the theta, we can find the Cp very easily, and this is also, we can find Cl, we can find Cd, and we can find L by D ratio also. So only requirement is the local deflection of the hypersonic flow at the surface. Now we know the theta, so we can find Cp and we can find Cl and Cd also using this thing. Remember this theta and alpha are two different concepts, two different parameters. Sometimes they are same, sometimes they are different. So these alpha and this alpha angle of attack depends upon the final resultant force after finding the Cp, and these are local forces, these are local things, so they are not same. We have to be careful here when we actually deal with the 3D body. We have to be very, very careful, and this is again cot alpha all the time. Now let us just try to use the same thing, infinitely long flat plate analysis. We just apply the whatever we have found, and then we have plotted this. So let us just discuss the plot of the results found using Newtonian theory on a flat plate analysis. It's infinitely long, so the one dimension is infinitely long, so the length itself will actually give the idea about the area. So that this is actually you can say this is infinite wing. The two sides are not being visible, which are just infinitely long, so only one dimension is visible. Here is the plot. We get a plot like this. So we have something like plotted L by D ratio, Cl and Cd all are plotted here. We have this hypersonic Mach number, and this angle alpha is the angle of attack. Cd is plotted here, and Cl is plotted here, and L by D is here. This trend is visible. Let us just discuss the trend. What are the students should observe this? There are just three plots are there: Cl, Cd, and L by D, and these trends are. We'll just see there. Basically, the three salient features we must remember whenever we see this graph here, and these salient features are: it's infinitely long span flat plate. Salient features are, so L by D decreases with alpha monotonically, and L by D becomes infinity as alpha goes to 0, but actually L by D is 0 as alpha is 0. Let us just see the picture. Look at L by D. L by D is actually decreasing as the alpha is increasing. It's very simple. Looks like when the alpha becomes completely vertical, 90 degree, and when the plate becomes vertical, so it's just directly coming. So in that case, all will get the drag. There is no lift available. But when the alpha becomes 0, we try to become as almost parallel to the flow. Ideally speaking, and following the law of Newton's theory, we should get the infinite L by D ratio. That is something surprising, but this is an ideal case, and normally it doesn't happen. We know that very well. And in the actual case, actually this becomes 0 because we consider the viscosity also. Viscosity cannot be ignored. So because the viscous drag and everything, viscous friction, all the at the 0 degree of alpha, this becomes 0. Ideally it's infinity, but this is not the fact. Second observation we make here is that the lift curve peaks at about alpha 55 degree. So we saw that a lift curve is going high, and initially it started increasing. So at the very at some particular angle it becomes the maximum, and then start decreasing down. So this actually happens something like 55 degree in the plot. As per the Newton's law, you have found that, but actually it is happening so 54.7 degrees. So which is a close agreement. This is actually gives the usefulness and the validity of the Newtonian law, because they is actually giving the result which is very, very accurate, and it's very close to the experimental result. Here is this picture. You can see that when you go here, something like at this is the peak value, something like going there. So somewhere here is something like 55 degrees, something like 45, something 60 degree, it becomes maximum. And that's what is somewhat actually found in the experiment also. The third observation we can make here is that at nearly 0 to 15 degree, the variation of CL with respect to alpha is non-linear. It's very non-linear. This is graphic representation of the non-linear nature of the hypersonic flow. So we actually started this module by talking about non-linearity of the hypersonic flow. That's very much comprehensive idea. We can actually understand that the phenomena involved are very complicated, so we cannot expect a linear relation. And we also see the behavior of the lift with respect to alpha in the very narrow region, something 0 to 15 degree, is very, very non-linear. You can see that it's non-linear. It's non-linear. In normal cases, in the low speed means subsonic as well as supersonic speeds, we get a linear relation. It goes linear way. Something like that's we know that alpha CL alpha curve is a linear, but here it's a non-linear. At the low angle, it shows a very non-linear behavior. Now let us just apply this theorem in a infinitely long circular cylinder and see how it is applicable and what are the values it gives. Actually, we have a CD will be given by d by qs. This is the definition of CD, and S the area. If it is infinitely long, that if you take the flow which is actually affecting the area, actually 2r, that is the radius, and the radius multiplied by the length, which is infinitely long. So we take it as 1 actually, and then we get CD is equal to 4 by 3. Let us just see how it actually has. Students can actually derive this thing, but I'm just giving some idea about how to do this. But we can remember that for the infinitely long cylinder, the coefficient of drag is actually 4 by 3. Here is a small the circular cylinder, and the flow is actually coming like this, and this is actually at locally it is making an angle theta. This theta is actually because of this this is radius, and this location is having a radial a polar inclination from the vertical actually theta, and this is also theta. So from the geometry, a student should clarify themselves, and they should be convinced that these angles are actually accurate. So if this is theta, this is theta, then this is theta also. Or you can say that if this angle is theta, then this angle becomes theta. This angle is actually the angle between the tangent and the flow direction, and that's what is our requirement, because this angle is actually going to be employed in the Newton's sine squared law. And then you take a small distance from here by making that as the elementary method we follow, that the small inclination of d theta, we get a small sign here, and then we can just write we can write Cp is equal to 2 sine square theta, and then this 2 sine square theta, and then a small the area on which it is working is actually that r d theta into 1. This is the r d theta into 1. So we can just in the entire analysis of the long cylinder is actually basically two things we should consider. One is the accurate measurement of the theta, and then you put the theta into equation of CD, and then the area on which it is acting, or the associated area, elemental area. This elemental area and the CP or CD and the dynamic pressure, the Q infinity, these all three will give actually the elemental drag, the elemental complete drag, dq, dd. And then for finding the complete d, we have to actually integrate with respect to theta from 0 to pi. Just this is the important thing we have to consider here. This if r is here, becomes actually 0. Then if r comes down here, then the entire angle from here to here will become actually pi. And we are not going to consider this angle. We should I think till now we have got the idea. We are considering the angle from here to here. Why? Because the location of the at which the flow will be attacking is going from here at this top position to the bottom top position. This area will remain shielded. So the flow is not going to impinge on this area. So this angle will not come into picture. So when you write this equation, the integration will be actually 0 to pi, and then we apply 0 to pi, we'll get total drag, and then we divide it by 2r in 2r, the area and the dynamic pressure, we'll get the value of CD, and CD is actually 4/3 in the case of cylinder. For the integration, the method of substitution will be required. The student can derive itself. Now same thing we can apply on the sphere also. So let us see the sphere in the hypersonic flow, how it goes. In the case of a sphere, we again follow the same method. Something like CD is equal to d by q infinity into s. That's the definition of CD. And the area which is actually influencing the flow, or the flow is associated with, is actually not 2r into 1 in the case of like what we saw in the case of cylinder. It will be actually pi r square, the entire cross sectional area of the sphere. And then when we apply this Newtonian theory, I will find the CD is equal to 1, and this can also be found out. The same method we can actually follow, and that we have to again use the method of substitution for the integration, and once we integrate, we follow the same kind of value here. Here is the sphere, and this sphere is again something similar what we are having, but there will be little bit variation and little bit of change in the case of process, in the case of procedure we'll follow here. Is this is theta as usual, and then this theta becomes actually local deflection, and the CP remains same as we saw in the case of cylinder, 2 sine square theta, and hence the CD also remains same. That is the local CD, that is actually 2 sine cube theta. Now what changes here from the cylinder case is that the area involved, the flow which is impinging on particular area, is actually not the particular area here, and then we just take a small area r d theta and then multiply with the 1, because it is actually 3D body. That is not the cylinder case was actually 2D body. In this case, the area will be actually, you can say that one whole strip, one whole ring is here. This ring, this is the radius, and this ring will be active working here. So the ring will have the radius actually r. If this is theta, this is 90 minus theta, so it becomes actually r cos theta. The ring will have radius of r cos theta, and this ring will have a width that is equal to r d theta. So the area on which this deflection is acting this deflection or this flow is impinging and then getting deflected by this particular angle is given by 2 pi r into r d theta. That's the area. So that's the only difference between the sphere and the cylinder. Cp remains same, so the local CD also remains same, and then the area only changes, and then you put the area, and then after that we just use the method of substitution. And then we can actually integrate, and then we can finally find the CD. The CD actually equal to 1 in the case of cylinder. So again we follow the same method, like put the expression for CD in the drag equation, integrate it for the frontal half portion of the sphere. Remember last time we did this for the frontal half portion of the cylinder. Now we do the frontal half portion of the sphere, and then we integrate it. For the integration, the angle of integration, the limitation will be, again we can see that. Let's go back and see that the angle will be actually this theta will vary from 0 to pi. The student have to be careful. They should not actually go from 0 to I'm really sorry. This will be 0 to pi by 2 from here to here. That's it. So by the time it goes from here to here, the entire frontal half will be covered. From 0 to, when it is 0, it will be here. When it becomes pi by 2, this thing will be here. And this is a ring. This is a ring. So entire surface on the frontal half will be covered when the theta varies from 0 to pi by 2. Unlike the case of cylinder where theta was varying from 0 to pi. And there also we are not taking any ring. We are just taking the small length r d theta, and then we are multiplying with the length of the cylinder. Here we have taken a ring. This ring will cover the entire frontal area of the surface area of the sphere if we just take the integration of theta from 0 to pi by 2. That's the limit of integration, and then we get the CD is equal to 1. Now there is another theorem coming here. We saw very easily that the high speed Mach number or something like in the hypersonic regime, the Cp becomes independent of the Mach number. So this is actually a very interesting fact that when the Mach number stops affecting these parameters. So we just have some kind of definition for the, and in a principle we call it Mach number independence principle. Students should remember this statement by heart, word by word. Hardly 3 to 4 sentences are there. Just remember this. I'm just reading it. It's interesting to note that above theory and the results so obtained don't explicitly depend upon the Mach number. Implicitly, it is assumed that Mach number is very high enough to prevail. So we believe that Mach number is very high, but its Mach number doesn't appear inside the theory, inside the equation. It is Mach number actually affecting it through a thin shock layer. Unless the Mach number is very, very high, we'll not get thin shock layer. Unless we get a thin shock layer, the situation and the flow impinging and going parallel to the surface will not depict to the Newton experiments or the Newton analysis. So Mach number is affecting, but implicitly. Explicitly, it doesn't appear in the equation. That's very clear. So beside that, precise value of m infinity doesn't enter in any of the above results, so to affect them directly, this is in unison with the Mach number independent principle, which states that this is the statement of the Mach number independent principle. The Mach number independent principle, which states that certain aerodynamic quantities become relatively independent of Mach number if m infinity is made very, very large. So Newtonian results are the epitome of this principle. The perfect example. We can see that Mach number is affecting, but indirectly and directly it doesn't affect anywhere in the entire relation. Now we saw that Newton's law is applicable here, and then we just try to derive the relation also, but something is missing there, because it's not like always when you have this Newton theta is equal to 90 degree, we get the maximum value, but this maximum value is not same all the time. definitely Mach number has to affect there. So the Newton's law was modified actually, and modification was given by someone called Lester Lees. Now the modified law can be actually summarized in a very in short sentences. So the equation Cp is equal to Cp max sin square theta along with Cp max is equal to limit m infinity m infinity tends to infinity Cp max is called modified Newtonian law. And some silent feature of the law, let us just look into the law, how it actually affects. The modified law is no longer Mach independent. When when we saw that in a straight Newton law it was not modified, that law was actually Mach independent. Only Mach number was there affected implicitly, that high Mach number only gives the thin shock layer. So at that thin shock layer only stimulate or depict the idea of a flat plate being impinged by the fluid particles. So it is actually affecting, but that was not nowhere close, and it were not at all available inside the equation. But the modified law is no longer Mach independent. It's affecting, and the effect of Mach number enters into it through the Cp max, which is Mach number dependent. So this ratio is actually depending upon the Mach number, and there are Mach number also available because of the dynamic pressure here. The second feature we see that as the Mach changes to infinity and gamma is to 1, the modified law takes the shape of Newtonian law. We already discussed this thing. So this looks like a flow of solids. A lot of solid particles are flowing. That will give the value Cp is equal to 2 sin square theta, because Cp max become equal to 2. Here is a small plot that we have made depending upon this modified law. When the gamma is equal to this is the various gammas are here. When the gamma is equal to 1, that is the upper one, it's actually making asymptote with the 2. So value becomes almost 2 actually at the Mach number 5, 6 and 7 here. For lower gamma, this doesn't go that side here. So it remains a little bit lower. This Newtonian law and the modified law was applied on a blunt nose body, and this is the result which has been found actually. It has been found that prediction of pressure distribution over a blunt nose body, it's the modified Newtonian law which is considerably more accurate rather than the straight Newtonian law. Now this is illustrated in the figure given here. The pressure distribution over a paraboloid nose section of Mach number 8 is estimated first by using exact finite difference solution of the blunt flow field, and then straight and modified Newtonian laws were used to do the same. They all are shown in the plot. Now the solid line give the finite. This is the solid line. Solid line give the actually the finite difference method. So solid line give the finite difference solution. So that exact solution is there, and the dotted line give the straight Newtonian law without applying this Cp max concept. We just use the value of 2 and we found it. So this gives the actually value. So there is small differences, and then when the modified Newtonian law was utilized, it matched amazingly with the exact solution to that. The dots are the modified Newtonian law. It actually matched 100% almost. So that's what is the modified Newtonian law and the straight Newtonian law. We'll just see the other method in the next video session, and we'll deal with the tangent wedge and a tangent cone method, which is the another method in the case of local inclination method to analyze the hypersonic flow. Till then, goodbye. Thank you very much.